Hello, my name is Mr. Sierfos Miller, and welcome to the Honors Geometry Semester 1 exam review. I'm going to go over the next however long this takes, we don't know yet. We're going to go through some problems and problem types from the exam, and we're going to talk about just general concepts and stuff. I'd like to thank anyone who is joining me live. If you have any questions at all during this presentation, please feel free to put them into the chat, and then I will do my best to answer them. I've got it right in front of me, so it should be fairly straightforward and easy to get us going. So if you're ready, I'm ready. I'm not ready, but we're going to do it anyway. You got your tea? Lace up your sports shoes. Let's begin. So you see above me, we have two parallel lines. We have AB, we have DE, and a transversal that cuts it CF at points C and F. So, there's a couple things and a couple properties to keep in mind with parallel lines cut by a transversal. So, we have the angle ACF and the angle CFE. Those two are equivalent angles. So, let me make... How do I want to note this? So, let's make like a square or something. Squares are sweet. Oh, everyone loves square. I said square. Square, super. Square, super. Super. So those two angles are equivalent to each other. And let's get another color we haven't used. And then BCF, this angle here, and DFC are also equivalent angles. Okay, so, and it's fairly obvious, like, what pairs go to which in this exact situation. This large angle and this large angle are equivalent. These two small angles are equivalent to each other. And, of course, for whatever reason, that ended up being blue. Because why wouldn't it become blue just randomly for no reason? The wonders of doing this live, quite frankly. So, doing all this, we've got those. So now, these two, the pink ones, are equivalent through what is called the alternate interior angles theorem. So you have the alternate interior angles theorem. Wow, me talking. Oh, wow, we're getting viewers. Hello, everyone. We're doing math. So we have those. The blue ones are the alternate exterior angles theorem. The blue ones are equivalent through the alternate exterior angles theorem. So, I apologize that we're going to have loud typey. Why do I have the loudest keyboard on earth? Drink tea, feel good. Got it. So, pink interior, blue exterior. The reason it's called interior and exterior is literally because of the degree of the angle. You have two angles, obviously, when you're cut by a transversal on each of these arcs. You have a small acute angle and a large obtuse angle, right? And obviously, the interior, the smaller one will be the interior, and the larger one will be the exterior. Now, we also have a couple other little equivalencies. So I don't have points out there because I am smart. So let's make a point. Oh, nope, I said a circle. No, not save. Control Z. Sure, why not? You have circle and circle. And let's get some text. EF point G up there. And point H down there. Super. So GCB is also equivalent to these interior angles. ACF and DFH is also equivalent. Now, when you have a vertex like this, you actually have a couple things happening here. So because we have a straight line, right? I'm pointing at the screen. That's so useless. So because we have this straight line, we know that this arc is 180 degrees, right? And this angle and this angle, it's leaving and entering at the same angle. This is called the vertical angles theorem. Let's bump up the exterior angles up to a new thing. That should be pretty exciting. So vertical angles are basically angles like CFE and DFH, where they're across from each other on a single vertex. You also have EFC and CFD. These two angles are called a linear pair. All right. So one of these days, so what I should do, actually, now I'm looking at what we've got going on here. And this is pretty good. Let's take a thought. Let's take a second. Parse it. So, where is my second color? Is this my second color? It is now. Sure. Whatever, man. Whatever makes you happy, Square. Whatever gets you going. So yeah. So we have vertical angles, a linear pair, alternate interior, and alternate exterior angles. As far as cutting through a transversal, I think I'm just going to double check there's nothing crazy going on. Yeah, okay. So, that's fair. So, another thing to see, anything that is a vertical, or not a vertical, anything that is a linear pair, like I have here, obviously they add up to 180. And I'm about to butcher this word, but a linear pair is 180 degrees, and that makes them supplementary. I can probably spell that better. We're just this whole thing is literally just held together with glue and hope. So please be patient. As I'm getting through this. All right, let's get some water. It is dry as heck here, I'd like to point out. I don't know why. I have no idea why. So, yeah, so a linear pair is 180 degrees, which is supplementary. So that's something you need to know. Let's see. Let's say we added a line. Let's say we had a second line. And I make it red. And I run it straight through AD. Awesome. Now I have bonus line. Alright, I like bonus line. Do, 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 do. And this seems a little high to me. I have all this unused space down here. Can I just move this without like breaking everything? Like, is that? Oh, that was not what I was expecting to happen. Okay. Alright, cool. This is our life now. So, get used to that, I guess. Alright, so let's make some more points. Oh, I love making points. This is actually not bad. I should have used GeoGebra. I'm an idiot. Alright, cool. It's fine. We're too late. We're too far past this now. We're using this crap that I've decided is what we're doing. HG. I don't want to use I. We'll use J up here, and we'll use K down here. Awesome. So, let's say I've got this new line over here, JK. So, we need to take a look at relations between angles in this transversal and this transversal. Now, this is going to be like kind of a weird trick question that you're going to see on the exam. Wow, my bit rate's going crazy. So I'm sorry, got distracted. So a weird little kind of trick question is you're going to see something that looks a lot like this. I keep pointing to that. It looks a lot like this up here. So what you want to be sure is the angles on this line and the angles on this line have nothing to do with each other unless it specifically says it does. So the left line and the right line, nothing to do with each other unless it specifically gives you this angle here. And then they have a lot to do with each other. But that's triangles. We'll get into that in a little bit. I got a lot of people I'm seeing viewing. At this exact moment, do I have questions? Throw them in chat. I'll give you a hot second. That gives me a second for tea. How are we feeling? Is this fun? Do we like this? I like this. This is fun. This is nice. It's different. I don't know if this is normal, but hopefully. I'm not seeing any questions come up, so I guess at this point, let's move on. I can make a big box. Whee! Oh, that's fun. That's a neat. We're like I said, we're all learning all at the same time. So let's take a look. See here. Ah, perfect. Let's talk about triangles. Let's talk about triangles for a hot second. Oh, you know what's really not useful? What I was doing. Perfect. A triangle. We did it. Let's make a different triangle. I lied. Let's make... Ooh. Okay, here's something fun. Alright, so while we're playing around with this, you can notice what kind of triangle is this. It is an isosceles triangle, and I'm going to try to spell isosceles now. Sure. We did it. So, we have an isosceles isosceles. Yeah, sure, why not? We have a triangle. It's triangular. And then let's say I have what? There we go. And let's say I have this line. Perfect. I've made a line. So, and now let's label our points, live our best lives and try not to sneeze, but sneeze anyway. Or no. A, B, C. So, we have a triangle, ABC, and we have this line, DE. That's not right. Whatever, it's cool. So we have this line, DE, and let's say, for the heck of it, that this and this are equal, and these are congruent to each other. So we're saying that up top we have equality, and down there we have equality. Now, this brings a couple interesting little properties. ED and CB have to be parallel right now. ED and CB have to be parallel if these two are equal and these two are, congruent. If they're congruent, not equal. So, yes. So, if they are congruent, that means that those two are parallel. That brings a couple interesting little side notes as well. Let's make some tools, and I'm going to use my little squares. And we're just going to have some happy little squares, Maybe we'll make a tree. Anything's possible. I almost literally just put like Bob Ross right over there. Like just, for background, you have to have a little bit of background. I hope that you have some background in your house. I'm sorry I don't have any music. I didn't make a copyright free music playlist to have as background music because I just didn't spend the time to do so. And I don't want YouTube to destroy my brand new channel that we just made for this. So that would be really bad. But we're on Twitch, so anything is possible. So if all of these, then we have... Oh, no. I want my squares. Z. So again, these two angles are congruent. Now, these two angles are congruent to those two angles as well. And this is cool. We have this because of the alternating angles from parallel lines. Because if you just extend these, then you have two parallel lines cut by a transversal. Two parallel lines cut by a transversal. Isn't that neat? Oh, that is neat. Oh, I love when everything kind of clicks together. It makes me very happy. Wow, we're getting some viewers. Hey, welcome, by the way. I'm glad you decided to take a little bit of time and take out of your day, let me into your home and into your after school life. I hope you're having a great day. And I say hello to people and then like 3 people leave. The viewer count is weirdly stressful for when I'm doing this, but who knows? Anything's possible. If you're my students and you're here, I'm glad that you're taking a little bit of time to hang out and be with us today. So we have these parallel lines. We have these as like proportional sets of similar things. And this actually is another thing. So we have similar triangles. So this review's kind of bouncing all over the place. But that's because these diagrams we're making are extraordinarily versatile because they're going to show you things from multiple problems. So I'm pulling things I'm pulling things like from multiple questions at a time. I'm actually like looking at things as we're going through, and everything's going very well. Yes, Wit, I in fact do, and thank you for sticking around with me. So we can talk about all that later. Right now is math. So we have all this. We have these angles are all equivalent. These two are equivalent because this has to be an isosceles triangle based on the way we set it up. These two are equivalent because this line is parallel to this line because these are equal. These are congruent and these are congruent segments. Now let's try something a little different. Let's say, do I have the skills with which to pay the bills? Yeah. So let's just pretend for a hot second that this segment, these segments, and these segments were the same length. Okay? So, like, if I have up here, this is a length of, you know what's really useful? Having white text. Well, that's a length of 4. Then this is a length of 4. That's a length of 4. And that's a length of 4. So we have all of these 4s right here. So the total length, AC, is 8. And so AE is 4, EC is 4, AD is 4, DB is 4, and AB and AC are 8 each. Sorry, I keep touching my eye. Really got to stop touching my eye. So if that's the case, then our little line right here gains some special properties. It's now a midline. Okay? That makes D and E midpoints of their respective lines. And it means that ED and CB are proportional. What that means, and actually, even more specific, well, ED and CB were already proportional, but ED now equals 1/2 of CD. ED now is 1/2 of CD. Exactly, if this is the case, if this is the way we set it up. So if ED, let's say, was, I don't know, 3, CD would be 6. Think about it this way. You hear the word mid, you think half. And this is actually good, like, general testing knowledge. So if you see mid, or midpoint, midline, bisector, any of those things that mean it's in the middle, that literally means it's in the middle. And so, like, if you have, something is a bisector, it cuts something in half, and it says this full length is 8. The bisector does this. What's this length? You only have one number. You only have one thing to do with that number, and it's cut it in half. So it would be, if the big length is 4, the half is 8. In this case, if the big length is 6, the half is 3. Now, let's take a quick water break. Pro tip, by the way, always have water and tea while you're streaming. Water, because it's important to stay hydrated. Tea, because you're talking the whole time. How's my volume, by the way? Is my volume doing all right? I checked it a little bit earlier, but I wasn't sure how we were doing. And also, are there any questions on this diagram before I move over to parallelograms? I'll give you guys a couple seconds. Got my... All right, we're good. All right, perfect. I'm not seeing any questions. We have our drink of tea, which is whoosh. God, that's actually really fun. It's fun to watch. It's fun to stew. I'm just we gotta keep ourselves in happy little clouds. So, what do I want to do next? Parallelograms. You know what's a good parallelogram? Whoa. That was not what I intended to do. Can I rhombus? Do I rhombus? Am I John Rhombi of the Philadelphia Rhombus? Nope. Cool. Whoa, that is not what I was expecting. That looks fine. Sure, why not? Rectangle. I wanted a rhombus. You gave me a rectangle. You know what? This is why MS Paint is free. So let's make a transversal. Why not? You know, let's make 2. You know, let's just live our best lives. And just make all these things. So, boop. Let's do doop. Doop. So, let's go. This is going to be... No. Points of caps. Why does not have caps on? You ever realize that you could be smart? Me. Right now. Today. And then this can be point E. Why not? Let's live our best lives. So, we've got all this. So, parallelograms. AB and DE are parallel. AD and BC are parallel. It doesn't have to be a rectangle. Rectangle is just what we got, because that's what I paid for, apparently. So we have this rectangle here, and I've made 2 diagonals, AC and BD. Now, a couple really useful pieces of information about diagonals. Diagonals will always meet at a point here. They will not always be perpendicular, but they will always bisect each other. Point E is the midpoint for both AC and BD. Okay? What do I want to talk about here? So, how do we know that, though? I guess. So, let's say we have, and I'm just reading through this. So, how do we know, we know that AD and BC are parallel, but are they congruent? I guess is the question that I will be asking you on the exam. So, you need to be able to show that these are equivalent. Now, can I go back? No, 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 no. Why? Yes. Too far. We solved that problem. So, let's start with some definitions. Let's start and let's do a little bit of a proof. All right. So, AB and where's my vertical line button? It's parallel to DC. So AB is parallel to DC. All right. How are these vertical lines going to look in this font? Oh, they look great. Why are they lowercase? Oh, because it caps lock on. All right, we're learning. So we have AB is parallel to BC. All right, cool. I like that. And we have diagonal. And let's just focus on DB. Okay? But we also have BC is parallel to AD. Let's actually make there be a comma there. So AB is parallel to DC. BC is parallel to AD. So that's definition of a parallelogram. Okay? So what we want to do is we want to prove that our sides are congruent. They're not just parallel, but congruent. Now we have our diagonal AC. Okay? And we can just draw AC. We can draw DB. We don't need to, but we can. Because, this is what we want to do with our lives. So actually, let's clean this up just a smidge. And let's actually only have one diagonal to worry about. Sound good? I only want to have one diagonal. And I want it to be AC. Alright, so we have one diagonal and it's AC. So, we know that DAC, based on what we were talking about earlier, DAC, actually, hold up, does this work the way I want it to? Oh my gosh, I forgot that tool existed. So we know DAC, whoa, that's too excited. And ACB are congruent. We know that those are congruent angles because we have the alternate interior angles theorem. Right? We have alternate interior angles are congruent because AB is parallel to DC. AB is parallel to DC. So this right here, this little line segment we've made is a transversal. Notice how everything we've talked about over these last, I don't know, how long have we been here? Half an hour. Everything we've talked about for this last half an hour has been based on just that first little diagram we made, right? We're just talking about parallel lines, transversals, congruent angles. A big part of what we did this semester was taking angles, taking congruency, learning how to relate things between each other. And what you're able to do is piece that together to create a bunch of different things. And it's really cool, I think. I love, I really love math, unironically. It's one of my favorite things. And it's because everything builds on the previous step. Anyway, sorry, I got distracted. Where was I? Yeah, so we have those two as congruent angles. Okay? So, what we need now is, well, let's just do this. No. There we go. So here, though, ACD and BAC are also congruent angles, right? Those are also congruent, also because of the alternate interior angles theorem. So we have, do I have a, oh, I do, we can just use the tilde, that's useful. So right now we have, let's see, CAD is congruent to angle, CAD is congruent to angle ACB. And then actually, let's just do this in given. And then alt int angles. And then we have angle ACD is congruent to angle CAB. Again, alt interior angles theorem. All right, so we got all that. Now, here's something interesting. So we now have that. So let's look at the line AC. Now, there's a property known as the reflexive property. The reflexive property says that something is equal to itself. Now, that's really important in this particular case, because we want to prove that we have, I keep pointing at it, we want to prove that AB is congruent to DC and BC is congruent to AD. Now, we don't know anything about these other than that they're parallel to each other. They could be any crazy length that we want. Like, we obviously drew it this way, but you know, have that as you will. So, but AC, if I had two triangles, right, that I built this parallelogram out of, AC is part of both of them. It's the base of both of them. And so, AC is congruent to itself. And then that gives us, conveniently enough, what did I literally just hit enter on? Aha! So AC is congruent to itself, and that gives us man, I need like more lines. How do I actually, you know what? Let's just see what happens if I make a new line. Anything is possible. We don't know yet. So that gives us angle, side, angle congruency for triangles ABC and CDA. Let's see what happens. Come on, text. Do it. Gah. Do it. Oh, it does resize. Oh, that's useful. I'm so happy about that. All right. So, and it takes me a hot second because I'm watching the stream back. So I actually have like a weird little delay on that. delay starts with a D, not an S or anything like that. So we now have these triangles are congruent, right? And if these triangles, it's up there. So if these triangles are congruent, that means that congruent parts of congruent triangles are congruent, right? Congruent parts of congruent triangles are congruent. I know I'm saying the word congruent a lot. It doesn't sound like a real word anymore. That's okay. Nothing is real. So, that means, and this is actually very weirdly specific, so I want you to take a look right there. So, let's look at the actual lettering that I wrote for those triangles. A, B, C, C, D, A. Okay? Notice on A, B, C, we have A, the first angle, is the orangey one. On the second triangle, C is the orangey one. In the middle, we have B and D are right angles. And then last, we have these whitish pink, I'm not 100% sure what color they are. These whitish pink angles. The order that the letters come in on congruencies matters. Okay? When you're doing angles, so if you're looking at those angles, CAD, look at the first angle, CAD. That is the angle on vertex A. The middle letter is the vertex. The outer letters determine the legs of your angle. So CAD is this angle right here. It's centered at A with legs CD. The second one, ACB, centered at C with legs B and A. The order that these things is written in matters, and that's why it looks so confusing sometimes, because you're like, why don't we just say angle A? Why don't we just say angle B? Because we have whoa, almost knocked my mouse over. At angle A, there's two angles. There's two different angles. And we don't know, if you just say angle A, which angle are you talking about for angle A? That doesn't tell us anything. Now, if you just have, John Triangle in the middle, wherever, that's not a triangle. We just have, John Triangle in the middle, wherever, right? And you just throw a triangle in the middle, and we say, this is angle A, then yeah, angle A, that's fine. But if you have a diagram of any complexity whatsoever, you need the three-letter system. You can't just refer to this triangle. I mean, you could. Like, you could 100% refer to this triangle as triangle whatever. Like, triangle Q. Right? Like, this is triangle Q now, What are you going to do about it? Nothing. I have a Q triangle. But referring to this triangle as, I gotta get my color correct. Referring to this triangle as A, B, C, referring to it as triangle ABC is more descriptive. Now, if you're doing, some sort of madness, right, and you've got 30 triangles or 20 triangles and you don't want to label them, you can put somewhere, triangle ABC referred to as triangle Q, but that's like that's like college level stuff. And that's actually something I want to hammer in right now, and that's something we're going to be talking about a lot next semester is notation. Notation is a really important thing in mathematics, because it's the difference between showing what you're talking about and notation is important, because if you don't use proper notation, if you don't have things written in the correct way, then what you're doing won't make sense to other people. It's about conveying what you're trying to say to another person. You see me stumble over words constantly in class, even in the last hour. And that's because I frequently have a hard time conveying what I'm trying to say. I find that I tend to use like just nonsense words a lot of the time, and that's really frustrating for me as a person, because I don't know how to turn that off. So I do my best to explain what I'm trying to get for you guys. Anyway, and actually, oh man, that's like a notation. It's like a thing that they care about here at Vanilla Lake Resort. Let's see here. I think that's all trig. That's all trig. That's all trig. That's something else you didn't deal with. I really, the only other thing I guess I want to talk about, because there's only like one or two more things. I'd like to thank all of you, by the way, for being here and hanging out with me. Just kind of relaxing. So, we're all just hanging out. So, what we're going to do for this last one, we've gone over that. So, we went over parallel lines, interior angles, exterior angles, transversals. We talked about triangles. We talked about congruency. Last thing I want to talk about is similarity, and we're going to go over it very briefly. Alright, so let's see, I have this. Can I do, hold on, copy, paste? I can. Awesome. Woo, that's weird. What was that? So, let's look at these two triangles that I've just made here. These two triangles have the same shape, but they do not have the same size. They are similar, and so the main difference, and I want to get this in text, similar, same shape, congruent, same size. So, similar triangles have the exact same shape, where congruent triangles have the same shape and size. Not just the same size. So, congruency, there's like angle, side, side, side. All these nice things that we care about and we know and we love. Similar really only has like angle, side angle, and a couple other things. All the congruency all the similar ones really care about is the only thing you really need to care about for similar triangles for this exam is what is that word? I literally, why did I move this to the other thing? Cool. The only thing we care about is scale factor. So let's talk about scale factor. So let's say I've got these two similar right triangles. And let's make my text the right color. And we go, whoa! Oh, no, that's the correct thing to have happen. Perfect. So let's say this triangle here has a scale factor of 4. Or, no, I'm sorry. Doesn't have a scale factor of. Has a side length of 4. And this guy here has a side length of 2. Let's make my life significantly easier. So, and this is, let's say, D, E, F, A, B, C. So we have triangle ABC and triangle DEF. All right. So we have these two triangles. ABC has this side, which is length 2, this side, which is length, and DEF has this side, which is length 4. And screw it, let's make it slightly more obvious. This is 5. This is 10. The scale factor between these two triangles, so ABC to DEF, ABC to DEF. Alright, that's fine. Is the scale factor is 2. We're multiplied by all of the sides, all of the proportions by 2. But the ratio is 1 to 2. The ratio, you start at 1, yes, that's how it works. You start at 1, goes to 2. So the ABC is basically 1 to this, which is 2. It works like a fraction. Don't stress on it. It's great. And that's all I really wanted to talk about for similar triangles. Like, honestly, I don't think you need anything else. Unless I'm forgetting something horrendously important, which is possible. Because that's how I've chosen to live my life. Forgetting things constantly. So let's see here. Pythagorean theorem. All right, last thing, everyone. Last thing, then we can call it a day. If you are, I misspelled Pythagorean probably. All right. So the Pythagorean theorem, a squared plus b squared equals c squared. The path, no, c squared. Aha! I have found you now this time. My nose is driving me crazy. So that's okay. Almost done. Almost there. Pythagorean theorem. Let's make a triangle. So, cool thing about Pythagorean theorem is Pythagorean theorem is something you only ever have to worry about when you have right triangles. All right? A right triangle is a triangle with a 90-degree angle. That was easy, right? So a 90-degree angle right triangle. And you have, and let's get the text to be right. You have side A, you have side B, and you have C. And you have angle B up there, C down here, and A over here. Okay, so notice angle A, side B, side B, angle C, side C. The side corresponds to the angle across from it. Alright? Alright. Sounds good. So, let's say we're trying to find a distance. Gotta come up with numbers. Let's say B is 4 meters. Sure, meters are a number, or a unit. And A is 3. Okay, so B is 4, and let's actually take this 4 and get it. Whoa, let's not do that. Oh, for the love, go away, 4. Thank you. 4. Now it's inside. All right, cool. That was driving me crazy. So, we have this length of 4, this length of 3. We need to find this length here, C. Okay? So, we would literally plug these into our Pythagorean theorem. So, that will give us 3 squared plus 4 squared equals C squared. Okay? So 3 squared is 9 plus 4 squared is 16 equals C squared. 9 plus 16 is 25 equals C squared. Alright. And now, in order to find this length, we just have to take the square root. And the square root of 25 is... That's right, random person that I heard through the internet. It is 5. Hey man, that's actually really weird. Like, these numbers came out evenly. Man, if only, like, 3, 4, 5, it was some sort of, like... some sort of, like, special thing that had, like, a name. That was less smooth than I wanted it to be. 3, 4, 5 is what's called a Pythagorean triple. It's basically a known set of whole numbers that when you have a right triangle of sides of that length, or any triangle of sides of that length, you get a right triangle and it fits the Pythagorean theorem. I think like 5, 12, 13 is another one that I know off the top of my head. We'll talk about it more next semester, and it's not something you need to know right now. So really just take that knowledge that you just gained and then you just throw it away. It's gone. Until later. Sounds good? Sounds good. So now we have this math. Let's throw that away. And let's pretend we didn't know what that number was. But we do know what that number is, but let's pretend we don't. And let's actually solve. Let's say we have the hypotenuse. And we have this leg here. Let's solve. All right, so we have the Pythagorean theorem. Again, a squared plus 4 squared equals 5 squared. So T. So, I'm sorry, I really need to get like a bumper for my microphone. That's on my ever-growing to-do list. Anyway, that's the point. So we still have a squared plus 4 squared is 16 again, and equals 5 squared, which we know is 25. All right, cool. We're cool with that. Now, we need to solve for a squared. So we subtract the 16 from both sides. So we have a squared equals 25 minus 16 conveniently comes out to 9. And then the square root of 9 is 3. Is there anything else that I really want to talk about? You know how transformations work at this point. I'm not going to waste your time. I'm not going to waste my time. If you are still wanting a little bit more on that, I linked a fantastic series of videos in the study guide. I don't have anything else for geometry. Parallel lines, triangles, Pythagorean theorem. Those are the major hits that I wanted to cover tonight. And we did it in like about an hour. So I probably could have done this. But it's okay. So I wanted to hit this. I'm going to throw this up on the YouTube channel that I linked to in the description. If you want to, this is my personal Twitch page. So if you want to throw a follow up on this, you'll get periodically annoyed by whatever ends up happening there. Past that, thank you all very much for taking some time and having me yell math at you outside of school hours. First period students, I will see you bright and early tomorrow. It is actually getting a little late for myself. Fifth period students, I will see you second exam Thursday. Do I have anyone who has any questions?